3-2, number 13.
3-2, number 13. Let's see what 3-2, number 13 is. Number 13. Find the slope of the function's graph at the given point, then find an equation of the line tangent to the graph there. So the function g of x equals x over x minus 2, and we're at the point 3, 3. Okay, let's see what we get. G of x equals x over x minus 2, and we're concerned about at the point 3, 3.
Is that number 13 on 3-2?
Yeah, maybe. Maybe that's just 3, 1. Maybe I turned back too far. Yeah, I turned back too far. My apologies.
Oh, you're fine.
Number 13 here. fx equals x plus 9 over x. And we're doing something at x equals negative 3. Excuse me. In 13 through 16, differentiate the functions and find the slope of the tangent line at the given value of the independent variable. So it's almost the same type problem, and it's almost this. Numbers differ a little, but it's really precisely the same method. Fx equals x plus 9 over x. F of x equals x plus 9 over x. And we're concerned about at 3. Let's throw 3 in here and see what we get. 9 divided by 3 is 3. 3 plus 3 is 6. So the point we're concerned with is 3, 6. But x equals 3. And let's find the derivative. F prime of x is, what's the derivative of x? This is x to the first, so it becomes 1 times x to the 0, so it's simply 1. This we can do one of two ways. We can think of it as a quotient, the function 9 over the function x, or we can think of this as 9 times x to the minus 1. If we think of it as 9 times x to the minus 1, the exponent is minus 1, comes out as coefficient, over or times x to the minus 2, which would be 1 over 1 minus 9 over x squared. Now in particular, at the slope at x equals 3 is 0. 3 squared is 9, 9 divided by 9 is 1, 1 minus 1 is 0, so the slope is 0. So it didn't ask us to, but if it asked us to write the equation of the tangent line, the equation of the tangent line with the slope of 0 is just y value. So the tangent line is y is equal to 6. Other questions? Yeah, let's see. Still have some papers that haven't been claimed. Buckley, Lake, Mitchum, okay. We've been looking at the derivative as a function, and because, you know, I mean, we start with the function, we take its derivative, the derivative is a function, and it has the same properties as any other function at that point. But let's begin with reviewing section 3.3, and basically we're developing rules for finding derivatives, so let's write down some of those rules. So if I have f of x and f prime of x, then for f of x, the definition is the limit as h approaches 0 of f of x plus h minus f of x over h where that limit exists. And we applied it to quite a few conditions. The derivative of the constant is 0. Derivative of the constant times the function is the constant times the derivative of the function. Derivative of sum is the sum of the derivatives. Derivative of a difference is the difference of derivatives. And for product and quotient, it changed a little bit. For the quotient, f times g, derivative is f prime g plus f g prime. And derivative of the quotient has one caveat. That caveat being we can't, why did I say q? Because I said quotient. That caveat being that g cannot be 0. But it is derivative of the numerator times denominator minus numerator times derivative denominator divided by the square of the denominator. So then we develop a few more. The first group we looked at, or the first one, was power rule for n being a positive integer. And we found that its derivative was n times x to the n minus 1. Then we empirically noticed that if n is a negative exponent, it seems to follow it. And we did the case of x to the 1/2, and it seemed to follow that rule. So we expanded that to include all rational exponents. And you realize between all rational numbers, there are infinitely many irrational numbers whose derivatives would have to be very close because the function is very close. So we have the power rule for all real numbers. X to the r is r times x to the r minus 1. R here. And there's only a couple more that we looked at so far. E to the x technically was first defined by saying I want a function whose derivative is the function again. So the function is its own derivative. We looked at that empirically. Again, we didn't prove it. We proved all of these, and this one we just kind of talked our way into, and this one we demonstrated empirically that the limit of e to the h minus 1 divided by h, that limit approaches 1 as h approaches 0. And we applied it, the same empirical argument we did at 7 to the x, but it doesn't have to be 7, it can be any base, b to the x. And we get back e to the x, but it's altered by the logarithm of the base, the natural logarithm of the base. So we have those rules. Well, those rules apply to quite a few things, but not everything. So we're going to look at, a little later this evening, we're going to look at expanding our rules on derivatives. But we're going to begin by talking about a little bit of physics, but it applies to business and biological sciences and the social sciences and everything that talks about rates of change. So, in general, it has its easiest, I think, application in physics, talking about displacement. Or position. Velocity, what speed, and also acceleration. And we'll demonstrate that the rate of change of displacement is velocity. The rate of change of velocity is acceleration. And there's another term that we toss in here for you physics nerds. The rate of change of acceleration is called jerk. Interesting term. But before you can start from rest, you have to jerk to get into some acceleration. then the acceleration can remain constant the rest of the way if you wish in many applications. But anyway, in most cases, we're concerned about those three. So if I draw a graph where we have displacement and time. Oh, and by the way, the difference here, velocity, the difference between velocity and speed. Velocity is technically a vector quantity. It has a magnitude and direction. 70 miles per hour to the north is not the same as 70 miles per hour to the south. If there are two vehicles both traveling in the same lane, going 70 miles per hour to the north, they maintain a constant separation. But if two cars are sharing the same lane, and one's 70 miles per hour north and the other 70 miles per hour south, we may have an issue. Unless they didn't achieve the 70 until they're already on the other side of each other. So, speed is magnitude only. So as you go around a curve, your velocity is changing even though your speed may be constant because the direction of that speed is changing. Okay. And acceleration also, you can have a vector position or a scalar position. You can have a vector velocity or a scalar speed. You can have a vector acceleration or a scalar acceleration. They don't really give an alternate term for acceleration, but it's also a vector quantity. Okay, normally the acceleration is in the direction of the path, but not always. And we'll look at one of those here in a little bit. Okay, so we may have some initial displacement, and we may have some kind of velocity which is changing over time. And we can find the average rate of change over that distance. This position, subtract this position, divided by this time, subtract that time. Just like always before, what we call the average velocity is the average rate of change with respect to time. So we have displacement often S, V, A. So S1 minus S0 over T1 minus T0 is my V bar, my average velocity. And if I draw a velocity graph, again, I may have an initial velocity, or I may start from 0. Okay. If you think about it, there are a lot of velocities we don't measure, because even if your car is parked at home in the driveway, it's really moving pretty quickly. Because at our latitude, we're moving about 800 miles an hour to the east because of the rotation of the Earth. And at the same time, the Earth is galloping around the sun at an incredible rate. The sun is galloping through the galaxy at an incredible rate. The galaxy is closing with Andromeda galloping, and also the two Magellan clouds. They will, the clouds of Magellan will crash into our galaxy in about 3 billion years. Andromeda will crash into our galaxy in about 4.5 billion years. Okay, having said that, I'm not worried too much about either one of them. I'd be really, really old if I'm here to see them. And two, you have to remember how much space there is between objects in the universe. So even if two galaxies are passing through one another, there's a relatively small number of collisions. although there's quite a few alterations in orbits caused by it. When all those motions are going on, we're concerned with disregarding most of them and only considering local motions. Even when we toss something through the air like that, we don't worry about the difference in gravitational attraction here as opposed to here, because there's a slight difference, and difference in gravitational attraction due to being closer to the center and further from the center, and the fact that the Earth is curved and the Earth is rotating causes Coriolis, and the drag coefficient of the object floating through the air. Okay. You know, just take a styrofoam ball size of a baseball and a baseball and take it to a stair landing, has good view. And what Galileo said, you know, all things fall at the same rate. Let go of those and see which strikes the floor several stories below first. Well, the baseball will. So clearly, if they're under the same acceleration, why don't they strike the ground at the same time? And the answer being, coefficient of drag. You know, they're about the same diameter, same shape, so their drag coefficient is about the same, but mass-wise, the baseball is much heavier than the styrofoam ball. So the negative force, because of drag, decreases the velocity of the ball a lot more quickly than it does the baseball. Okay, but same thing over here. If we have velocity, you know, and positive velocity and constant velocity, then we stop and we're behind a semi-truck and he puts his backup lights on, the horn starts sounding, and you know you're too close, you can't see in the mirrors, so you put your car in reverse and back up some until you can't back up anymore, and you hope he stops before he crunches, and then you, after traffic clear, you know, so you can have positive or negative velocity, just like you have positive or negative displacement. You can be on either side of your starting point, displacement-wise. So here we have velocity and time, and units are commonly miles and hours, or feet and seconds, or meters and seconds, or kilometers and hours. Over here is feet per second and seconds, or miles per hour and hours. And then we grab acceleration as well, but let's look at a simple, I say simple, acceleration problem, velocity problem, and define both velocity and acceleration. So S is equal to its initial position plus its initial velocity times time plus 1/2 AT squared, where S naught, V naught, and A are constants. This is about the simplest model that we can have for position under a constant acceleration. So velocity, ds dt, rate of change of position with respect to time, is velocity is equal to v naught plus at. And the rate of change of velocity with respect to time is the second derivative of position with respect to time twice is acceleration. And that's what we get under uniform acceleration. Well, where do we have uniform acceleration? And the answer again is, we model it well. A gravitational field provides a uniform acceleration. If we just disregard all those things we need to disregard, that Gravitational attraction is dependent upon position. And by the way, for instance, if I let it go here, because it's closer to me, gravitational attraction has to me has greater effect than if I let it go out here. But as it goes out here, the gravitational attraction of this to you guys is increased, whereas mine has decreased. Are those enough to measure? In theory, we know those values. In practice, we can ignore them. Okay, so let's do a numerical example. Let's keep these up here, so I'll erase at this point. There are a couple of diving events in the Olympics. One is springboard, the other is platform. Let's do the platform diving, so it's much easier. How high is the platform? Above water surface. Anybody know? Any divers in here? Anybody watch the Olympics ever? That's 10 meters. Okay. Now, depending upon the dive, they jump a little. Usually their jump is not very high, but let's assume they just fall. Just step off the board, so to speak. How long does it take for them to hit the water? And at what speed are they traveling? Well, since this is metric, 10 meters, helps to know that the acceleration due to gravity, commonly called G, in the metric system is about negative 9.8 meters per second squared. Okay. So, and it follows that model over there on the right-hand board. Position is the initial position, 10 meters, plus the initial velocity, 0 times time, minus 1/2, 9.8, 4.9 t squared. Okay. So I want to know how long it takes for him to impact the water. Okay. So we know that if this is 10, then we'll start, this is 0, this is 10. So 0 is equal to 10 minus 4.9 t squared. That is 4.9 t squared is equal to 10, or t squared is equal to, I'm going to write 100 over 49. Okay. So it comes out nice. Doesn't that come out nice? And then t equals 10/7 or negative 10/7. How can it equal to negative 10/7? And when would that ever be important? Well, being an old artillery officer, that negative 10/7 is also important. Because if someone is lobbing something out to me and I pick up their trajectory about there, okay, and you observe the trajectory of the impact, you'd like to project the trajectory back in time so you can surmise its point of origin, so that you can have your friendly neighborhood bombers and friendly artillery fire discouraging them from continuing to fire at you. That's a problem that most of us don't have to deal with. And now the military is pretty much automated they observe something inbound coming in, and their radar back calculates automatically. It's programmed to do that. And they'll say, oh, we believe it came from there, so that you retaliate back to the point of origin and discourage them from either continuing firing from there or encouraging them to move away quickly. Okay, so that's kind of where the negative would be. So it says, if somehow I was Aquaman and negative 10/7 of a second ago, I leapt from the water at enough velocity to reach that height before turning and falling back down to re-enter the water a positive 10/7 seconds, or total of travel time 20/7, almost 3 seconds round trip. Okay, so on this application we're not concerned about the negative. We accept 10/7 seconds as our result, and the question is, how fast did we smack into the water? Okay. To find that, I need to take the derivative. Velocity is derivative of this, which is minus 9.8 t. At time 0, the velocity is 0. At time 10/7, velocity is negative 98/7, which turns out to be rather nice. 7 and 98 goes 14 times. I'm sorry, 9.8, so 1.4 meters per second squared. No, I was right the first time. Sorry. I'm down. Negative 9.8 times 10/7 is 98 over 7, which is 14 meters per second squared. Okay. And that's a lot faster than you think, because that's about almost 15 feet per second. And doing a little arithmetic, that's about 10 miles an hour. Is that right? 10 miles an hour? Is that about right? No, I'm sorry. This is about 15 meters per second squared. 3 times that, so it's about 45 feet per second squared. Okay. And that is more like, over 30 miles an hour. Okay. Now, having said that, 30 miles an hour is kind of the threshold. If you fall off something and you're traveling 30 miles an hour, when you splat into concrete, chances are you are going to die. Okay. Here, however, you're not splatting into concrete. Hopefully it's liquid water. Unless you're foolish enough to do this in the wintertime when this is frozen solid. So, you don't have to be very high before it becomes a fatal distance. If you know how to hit and roll, you stand a better chance of surviving. Okay. So, that's an easy enough application. Let's make it a little different. You're in a snowball fight, which you may have the opportunity to do tomorrow. What's the latest weather predictions? Anybody? So you're doing this in classic fashion. You're standing here, lobbing snowballs this way, Another person standing over here. Lobbing snowballs back at you. A good strategy that sometimes works. When someone throws a snowball at you, you have to mentally observe that path, decide where you have to be in order not to get hit by the snowball. Okay? So, rather than throwing here, if you throw here, it takes longer for them to decide where that path's going to take that snowball. So while they're busy doing this, you throw the fastball. You can fool them once with that, but you know, maybe hit him square in the face with it, usually the game's over. So, and this is called high angle fire. Kind of interesting. That things more than 45 degrees are regular fire. Things above 45 degrees are called high angle. And let's say that you're at 30 degrees here and 60 degrees. If you release at the same velocity, then this trajectory and that trajectory will coincide at the same level as the release, but not at the same time. Low angle fire takes much less time than the high angle fire. Interesting enough. So let's get down the realm of snowballs. Being a former artillery officer, if I'm firing a cannon at 30 degrees with a muzzle velocity of 1,000 feet per second on level terrain, essentially an altitude of 0, impact point at 0. This follows some path. I want to find a couple things here. One of those things I want to find out is the range. That is, how far will this go before it smacks into the ground out there? The other thing that's sometimes important is max height. Let's solve both of those, given that this is flat earth problem, no air resistance, no Coriolis, no aerodynamic lift on the projectile. So it follows the model that we've already put up, except now we're in feet, so we'll use SAE standard American engineering units, where G is now negative 32 feet per second squared. And we have actually two sets of equations. We have a vertical set and a horizontal set. The vertical set has an initial position and initial velocity times time, and since we're in feet per second stuff, minus 16t squared acceleration component. But horizontal is independent of that acceleration. A reasonably simple demonstration of that change in bank went on. Reasonably simple demonstration for that is you take a couple of coins and get them so they depart the end of a table at the same time, but one has a higher velocity, horizontal, you'll see they strike the floor at the same time. So, horizontal motion has an initial position and an initial velocity. Let me put v sub y here, v sub x times time, but no acceleration. Now realistically, yes, it slows down because of air resistance, but I said we're ignoring that. Okay. And for a reasonably heavy projectile, that's, you can ignore quite a bit of air resistance. On the other hand, if you're trying to shoot a feather, you fire a feather out of something at 1,000 feet per second, within about a foot and a half, it's already slowed down to almost nothing and flutters to the floor. Because the drag coefficient compared to the mass is huge and stops it rather quickly. So, here are the equations. I'll say x and y are both 0 here. So, and y is equal to nothing plus v sub yt minus 16t squared. And here, x is equal to nothing plus v sub xt. So the question is, what is v sub y and v sub x? Well, if this is 30 degrees, trigonometry, the vertical component is the sine of 30 degrees times 1,000 feet per second, or 500 feet per second. The horizontal component is the cosine of the angle, cosine of 30 degrees, about 0.866 to 3 decimal places, times the muzzle velocity. That means it's about 866 feet per second. So let's first solve the vertical equation. V sub y is 500 t minus 16t squared is the general equation. And it begins at 0. I also said that, flat earth, so what's the y value down here? Also 0. Do the arithmetic here. Factor of t, let's see, t times 16t minus 500 equals 0. T equals 0, or t equals 500 divided by 16. This goes 32 and a half, I think. So, this projectile is in the air 32 and a half seconds before smacking into the earth. Now let's find the range. Initial x position 0. The initial x velocity is 866. The time is 32.5. Someone will multiply that out. Still might be on my number cruncher from this morning.
On that first one, it's 31 1/4. 500 divided by 16.
Let's see, 16 goes in 480 30 times, leaving 20. So 31 1/4. Oh man. Okay. $31.25. 31.25. Thank you.
I cheated, I had to calculate.
Well, you know, like I've mentioned, and I'll mention it many more times, I can do arithmetic incredibly quickly in my head, and sometimes I get the right answer. So I appreciate it anytime you correct me. So having said that, 866, well, let's clear all this. 866 times 31.25 is 27,062 and a half feet. Copy that right there. 5 miles. Okay. Give or take a little bit. So, how long does it take sound to travel from here to there? You know the rule of thumb when you see lightning and then hear thunder? You count. 1,001, 1,002, 1,003, 1,004, 1,005. 1 mile. So, if you happen to see the muzzle flash, (1,001, 1,002, 1,003, 1,004). By the time you got to 25, you would then hear the boom, which would leave you a good 6 seconds to try to get out of the way if you thought it was coming toward you. A couple of ways to get out of the way. One, find a hole in the ground that's plenty deep and has cover over it. Two, how fast can you run? Because these things, if they throw that far out, you know, horseshoes and hand grenades and artillery, close counts. So you don't want to be too close. The closest I've been to a 250-pound bomb going off is about 20 yards. Closest I've been to a 500-pound going off is about 30 yards. But on the 30-yard one, I was in a bunker. And so when it went off, the two of us that are in the bunker together said, that didn't sound like it went off. But then our radio said, you guys all right? It lifted us 6 inches off the ground, and they were over 200 meters away, prone on the ground to be safe. So you don't want to be there. Came out of our bunker, walked over and said, yep. 7 feet deep, 20 feet wide, big hole in the ground. You don't want to be under. Okay. So about 5 miles down range, it smacks into the ground. How high did it go? Well, what is this? Those of you that remember your college algebra, what kind of curve is that? Second degree polynomial. Second degree polynomial is a parabola. And the vertex of a parabola is either its high point or low point, and the vertex occurs at minus b over 2a. Well, let's look. That's b. This is a 1,000 divided by 32, same as 500 divided by 16. Is that right? No, that's not right. Oh, over 2a. Minus b over 2a. So it's 500 over 32, which is half of this number. Take half of that number times, and put it back to this equation. We'll find out how high it went. So instead of 31.25, you put 31.25 over 2, square it, times 16. Do the arithmetic. Let's see what that is. Okay, 500 times 31.25 divided by 2. Subtract 16 times clean 31.25 divided by 2 squared. And that tells me is 3,906 1/4. So, in most cases, if you're trying to direct a fire out here on some target, and you know it's range, and you know they have computers for all that, but this is the path they'll choose. On the other hand, if you have terrain in the way, then you have to fire a whole lot of times to eventually punch a hole through here so that the next round goes and hits your target. Usually not the best way to approach the problem. That's when you change to, instead of firing at 30 degrees, you fire at 60 degrees, and you'll have the same result, but the time of flight will be significantly longer. Now, another time you might want to fire higher angle is if the target is elevated and you're down here. Low angle won't get there. I have to fire high angle to hopefully come down on target. So, kind of interesting. In business, you know, we call the derivative, another name for derivative is the rate of change of the function with respect to, in this case, time, but it's the rate of change of function often when we're dealing with x's and y's, the rate of change of y with respect to x. In the business world, we're often interested in how your money is changing with time, so they use terms called like marginal profit, marginal cost, marginal revenue. And the word marginal in the College of Business is the same as our word derivative. It's the rate of change of money with respect to time. Marginal profit. How's your profit changing with respect to time? Marginal cost. How are your expenses changing with respect to time? Marginal revenue. How's your revenue changing with respect to time? Revenue, of course, your profit is revenue minus cost. Your basic R minus C is equal to profit. Years ago, I came across 2 lemonade stands. One side of the street, they're selling lemonade for 50 cents a cup, and the other side of the street, the kid was selling for $5 a cup. I think his parents worked at Starbucks or something, I don't know. I had to ask. I went over and said, why are you trying to sell lemonade at $5 a cup? He says, all I have to do is sell 1 cup. He's made the profit that he needs to make for the day. Whereas the other kids have to sell at least 10 cups to come close to at least the same revenue, and their cost will be more because they will have had to use more cups and more lemonade. Now, you may scoff at that strategy, but back in the early days, what was the largest selling automobile in the United States? Ford Motor Company, Model T. Okay. Well, started a company, later becoming General Motors. Chevrolet was one of its branches, and Chevrolet made a competitor to the Model T. Okay. And because they had this assembly line stuff figured out better than the Ford assembly line, they could make a Chevrolet for less cost than it cost to make the Model T. So you'd think the market strategy would be, we can give you a good car for a lower price. Nah, they advertise, step up to a Chevy for a few dollars more. So the implication was, what they wanted you to buy into was, that their car was better, so you should be willing to pay a little more for a better car. And within very few years, Chevrolet became the leading automaker in the world, passed up Ford in production and sales. Not because their car was significantly better, but their profit margin on each car was better, which means they had more revenue or more profits to share with their employees and start making other cars as well and stuff like that. One time Hershey Chocolate Company thought they were so big that they could quit advertising, because advertising is a big expense. And in the year they were not advertising, they fell from _1 to #2, and that's when Nestle Crunch overtook Hershey bars as #1 selling chocolate bar. So they started advertising again. So for many years, Hershey was the largest chocolate company in the world, but then a very large German chocolate company bought out Nestle, and the combined company of the German company Beich, B-E-I-C-H, chocolate, and Nestle's chocolate became the largest. And now I think Beich has divested themselves of Nestle again, so I don't know what the deal is on them now. Okay. So, or you can buy, what is it, Godiva chocolate, or Giordano, what's that? What's the one you've seen advertised lately? That's Giordano's out of San Francisco. That's, yeah. For a few dollars more, you can have that. Is it that much better than Hershey? I don't know. You know, I've had that. It's not bad. You know. But, you know, do I want to pay $1 for a chocolate bar or $5 for a chocolate bar? I'll go with $1. Okay. Okay, enough about looking at derivative as a rate of change. Let's now look at adding to our derivative list. And what was one of the prerequisites for this course? Well, let's ask another one. What were the last 2 math courses you took before coming to calculus? Trig and pre-calculus. Well, trig. We have 6 functions we commonly work with in trigonometry: sine, cosine, tangent, cotangent, secant, cosecant. So let's find their derivatives. And I look over here, and none of these work. So I go back to the definition. So if f of x equals sine of x, and f prime of x is the limit as h approaches 0 of the sine of x plus h minus the sine of x over h, where that limit exists. So I have to recall some trigonometric identities. What is the sine of a sum? Sine of alpha plus beta. Sine alpha cosine beta plus cosine alpha sine beta. Applied here, that becomes sine x times cosine h plus cosine x sine h, that's this term, minus the sine of x all over h. I think I'll group the first and last terms together and factor a sine out. Limit as h approaches 0, sine of x times cosine of h minus 1 minus cosine x sine h over h. Still have all the terms. I think I'll break this into several parts. It is equal to, I'm sorry, plus sine x times the limit of, as h approaches 0, cosine of h minus 1 over h plus cosine x times the limit sine of h over h. Because the limit of the sum is the sum of the limits, limit of the product is the product of limits, limit of the product is the product of limits. So basically I grouped those together and grouped that together. Okay. And if you go back in your notes sometime last week, when we're or the week before, when we're looking at limits, we looked at each of these limits. And this limit, sine h over h, as h approaches 0, is 1. And this limit, as h approaches 0, is 0. So the result is 0 times the sine of x is 0, plus 1 times the cosine of x. That is simply the cosine of x. So we can add that on here. The derivative of the sine of x is the cosine of x. So for the other 5, well, for the cosine, we'll use the same excuse me, same method as again. We don't have anything for the cosine. So derivative of cosine is limit as h approaches 0, cosine of x plus h minus cosine x over h. Apply our trig identity for the cosine of the sum, limit as h approaches 0. Cosine of the sum is cosine of the first times cosine of the second minus the sine of the first times the sine of the second. That's this term minus cosine x over h. And as I did before, I'll group those two terms and write cosine of x times limit as h approaches 0 of the cosine of h minus 1 over h minus the sine of x times limit as h approaches 0 of sine of h over h. And just as before, cosine of h minus 1 over h, that limit is 0. And sine of h over h, as h approaches 0, that limit is 1. So we have 0 times the cosine of x, goes away, and 1 times the opposite of the sine of x. So cosine of x, the derivative is minus the sine of x. Now fortunately, we can now disregard the definition because the other four functions can be defined by ratios or reciprocals of what we already have. So the tangent of x is sine of x and cosine of x. And this is derivative of a quotient. Derivative of the quotient is derivative of the numerator, cosine x, times denominator, cosine x, subtract numerator, sine of x, times derivative of the sine, derivative of the denominator, derivative of the cosine is minus the sine, all over the square of the denominator. If I look at the numerator, I have cosine squared x plus sine squared x and cosine squared x. And what's the fundamental trigonometric identity? What's the Pythagorean relationship between sine and cosine? What is the number one?
Cosine squared plus sine squared.
The number one is cosine squared plus sine squared. So this boils down to 1 over cosine squared of x, which normally is written as the secant squared of x. So the derivative of the tangent of x is secant squared of x. And continuing along those strains, let's see. Cotangent of x is cosine x over sine of x. I'm about to sneeze too, so whoever sneezes there. Again, it's a quotient. Derivative of the numerator minus sine of x times denominator sine of x. Subtract numerator times derivative of denominator over the square of the denominator. Now the numerator is -1 times sine squared x plus cosine squared x over sine squared x. So now what's that numerator equal to? Disregard the -1 for a moment. What is that equal to? 1 times -1 is, so I get -1 over sine squared x, which we normally write as minus cosine squared of x. So, the cotangent of x is minus the cosecant squared of x. I'm going to erase this now, but I'm going to move back to the center board. How about the secant of x? definition of the secant x is the reciprocal of the cosine of x. I'll take the derivative of this as a quotient. So the derivative of numerator times denominator, subtract numerator times derivative of denominator over the square of the denominator over sine of x over cosine squared x, which I choose to write as 1 over cosine x times sine x over cosine x, which are secant of x times the tangent of x. So derivative of secant of x is secant x tangent x. And anybody want to take a guess at the cosecant? The cosecant, CSC of x, derivative 1 over sine of x, derivative, is equal to derivative of the numerator times denominator minus numerator times derivative of denominator over the square of the denominator, which is minus cosine x over sine squared x, which I choose to write as minus 1 over the sine of x times cosine x over sine of x, which is minus the cosecant of x times the cotangent of x. So we add that to our list. Derivative of the cosecant, CSC of x, is minus the cosecant of x times the cotangent of x. So our list is growing a little bit. Remember, the alphabet has 26 letters. We now only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Leaves 8 to go before there's 8, about 9 to go before we are as many as the alphabet. So, lots of room to add more. Okay. And what we're going to add in the not too distant future are logarithms, hyperbolic functions, and the biggie that helps a whole lot in many derivatives called the chain rule. But all those will be after your first exam. These are all the rules for finding derivatives that you will have going into the first exam. So before we get into working some problems in section 3.4 and 3.5, everybody get signed in? 2 of you in the back, or semi-back. Front left. Okay. So I have here pretest number 1. These are the concepts that you will need for exam 1. I would like to think between now and Wednesday, you'll do your best to solve these dozen problems. having said that, I also hope that you come to class on Wednesday, because our sole goal on Wednesday is to work through every one of these so that you fully understand each concept. And if you fully understand each concept and practice said concepts, then the exam itself should not be a surprise to you, and you should do well on it. If you choose not to practice on the pre-test, well, come on, I can count to 4 here. 1, 2, 3, 4. Lack of practice is often a self-fulfilling prophecy that says, I'm not going to do well on the exam. Some of you, because of your background, may be in pretty good shape for this first exam, but I would still encourage you to spend some time in the book and or online and or in the math lab and or in a study group of your peers as you work through these problems. Okay. In section 6.4, let's attack a couple of those. So I'm looking on page, what page am I looking at? Looking at page 150. And the first few, it gives us several things to do. A, find the body's displacement and average velocity over the given time interval. B, find the body's speed and acceleration at the endpoints of the interval. And C, when, if ever, during the interval, does the body change direction? So number 2 says S equals 6t minus t squared. S equals 6t minus t squared. And the interval it gives us is what, 0 to 3? 0 to 6. Okay. With t, element of the interval, 0 to 6. So, part A said, find the average velocity from beginning to end. And the average velocity is the difference in positions divided by difference in time. That is, I want S evaluated at 6 minus S evaluated at 0 divided by 6 minus 0. And this is my average velocity. That is, average rate of change with respect to time is that. Plugging in 6. 6 times 6 is 36. 6 squared is 36. 0. Plugging in 0. 6 times 0 is 0 minus 0 squared is 0. 6 subtract 6 is, 6 subtract 0 is 6. 0 divided by 6 is 0. So on average, he didn't go anywhere. I was here all day. Well, your average is not your instantaneous. So that's why I also said find your velocities and accelerations at beginning and end, didn't it say? B. Find the body's speed and the acceleration at the endpoints. Okay. So my speed or velocity is the first derivative of position with respect to time, which is 6 minus 2t. Acceleration is the second derivative of position with respect to time squared, or the first derivative of velocity with respect to time, and it is -2. So in particular, The initial velocity is 6. The terminal velocity is -6. The initial acceleration at 0 is -2. Final acceleration at 6, -2. So it's under constant acceleration. Okay. Just as if I toss this up and it comes down, that was under constant acceleration of gravity pulling downward. You notice that had an initial velocity at the release, and the terminal velocity at catching it is kind of like these situations. It was going as fast up as it was down under constant acceleration. And it said find the time where the velocity was 0. Well, let's solve that equation. V of time, function time, is equal to 6 minus 2t. We want to know when that was 0. Add 2t. T equals 3. So at t equals 3, the velocity was 0. Where was it? S at 3. Come back to S. S at 3, 18 minus 9 is 9. Now let's see, have we answered all the subparts? Part A, the average velocity over the given interval, which is beginning position minus final position divided by difference in time. B, the body's speed at beginning and end, and acceleration beginning and end. And C, when, if ever, during the interval does the body change direction? It changes direction when the velocity reaches 0. Now that's not always the case. Hopefully when you're driving here, after you backed out of your parking space, from that point on, your velocity reached 0 several times when you approached a stop sign. STOP does not mean students tear on past or float through. When I was in high school, I was with a friend and we floated a stop sign onto north of Classen Boulevard. Some of you know where that is, north side of town. And motorcycle policeman saw us, pulled us over almost immediately. My friend Lammy, nobody was close, so we turned. So the guy was, about to write us a ticket. It's about 9 o'clock in the evening. We're southbound. In the southbound lanes coming northward at about 10 miles an hour is a car driving without headlights, having trouble staying in its lane. And the motorcycle policeman, Lammy, and I all kind of watched the guy go by. Policeman says, "Stay here, I got to check this out." So he has him caught within a block. And we said, "We don't care if he told us to stay here. We want to see what he's saying." So we hopped out of the car and jogged down there and, said, "We're here, we're just watching." And he said, "Okay." And the guy saying, I know I've been drinking, officer. That's why I'm driving so carefully." And then the officer looked up and said, "This is going to take a while. You guys go on." "Thank you." That's a ticket Lammy didn't get. But the guy was being cooperative. 4 sheets to the wind, so to speak. So, just because you stopped didn't mean you changed direction. But here, if we enter any time from 0 to 3, short of 3, we have a positive velocity. Any time beyond 3, we have a negative velocity. So we did change direction at t equals 3. Okay. Number 9 is kind of interesting. fall on Mars and Jupiter. The equation for free fall at the surface of Mars and Jupiter, S in meters, T in seconds, are S equals 1.86 T squared on Mars and S equals 11.44 T squared on Jupiter, and I'm going to toss in Earth. Earth is equal to 4.9 T squared on Earth. How long does it take a rock falling from rest to reach a velocity of 27.8 meters per second? That is about 100 kilometers per hour on each planet. Let's see. 1.86, 11.44. 1.86, 11.44, and 4.9. Okay. T squared. T squared. T squared. These are all of the equation form. S equals S naught plus V naught T plus 1/2 AT squared, where S naught is 0, V naught is 0, and A is the associated G of Mars or Jupiter or Earth. So, S equals, S equals, S equals. Solving each of these, we want S to be, oh, what did we want? We want to know when its velocity. How far did it fall before it reached a velocity? Yeah. So, velocity in each case. Velocity on Mars is twice this. What's that? 3.72 T minus twice this. Velocity on Jupiter, negative 22.88 T. Velocity on Earth, negative 9.8 T. Okay. And what we want is, when do each of these reach 27.8? So we have three equations, three unknowns. 27.8 divided by negative 3.72, and that's 27.8 downward, so we can put a negative there as well. Is equal to T on Mars, negative 27.88 divided by, I'm sorry, negative 22.88 divided by, negative 27.8 divided by negative 22.88 is the time on Jupiter that takes to reach that velocity. And lastly, on Earth, negative 27.8 divided by negative 9.8 equal time on Earth. And if we use our calculator for each of these, what do we get? On 27.8 divided by 3.72, I doubled that, and we get 7.47 seconds, about 7.47 seconds. And on Jupiter, 27.8 divided by 22.88 is about 1.215, let's say. 1.215 seconds. And on Earth, 27.8 divided by 9.8 is 2.837. 2.837 is equal to time, ours. Seconds is our Earth time. And they tell us that is when you get to be 100 kilometers per hour, 100 kilometers per hour is about 62 miles per hour, which is about twice the speed to kill you, smacking into something solid. So on Mars, you'd probably be dead because it's solid. On Earth, even hitting water at 60 miles an hour, the chances of survival have gone down quite a little bit. Especially if you do a belly flop. It's like almost like hitting concrete. But on Jupiter, even though it doesn't take you long to get up to that speed, if that's the time it takes to smack into the surface, what is the surface of Jupiter? It's a gas giant. You know, you smack into gas. If you're in your spacesuit, you're still okay. Okay? Now, I don't know how far you would fall through that thickening gas before you eventually slowed down to essentially zero, and then you could swim in it. Who would think gas could be that dense that you could swim in it? It can be. Hopefully you don't get caught up in the giant red spot, because winds in giant red spot are in excess of 500 miles an hour. Might be a little rough. Okay. It all depends upon your accelerations. Okay. Now, having said that, how many of you could afford to weigh just a bit less? Most of us could. Some of us more than others. I'm only about 75 pounds heavier than I was when I was competing in gymnastics. Where'd all that come from? I'm the same height. I don't know. If you go to the equator, you weigh less than if you're at the North Pole or South Pole. If you go on top of Mount Everest, or even Pikes Peak, you're a little bit less than you are at the base of the mountain. On the other hand, kind of interesting, like I say, gravity is different in different places. If you're in Colorado Springs, you know, the second order model of the Earth is an ellipsoid, oblate spheroid. Okay. And when you're standing in Colorado Springs, you're not perpendicular to the spheroid, because basically you have to lean to the east to compensate for the gravitational attraction of the front range of the Rockies. You have to lean about 0.02 of a degree toward the east. Okay. Now, having said that, there are places in Sri Lanka that you kind of have to lean away from the Himalayas, and there you have to lean up to 0.007 of a degree toward the south in order not to fall toward the mountains. Anytime you walk up to talk to somebody, you actually have to lean a little away. Otherwise, if you're not paying attention, eventually you'll smack heads. Okay. How much do you have to lean? Throw in Newton's universal gravitation constant and you'll see it isn't very much. It's so much that it's essentially imperceptible. Well, I'd love to tell that story to go to a middle school class, pick a guy and a gal out in middle school class and say, you know, you two are attracted to each other. I mean, you know what that does to middle school kids? I mean, they turn about 14 shades of red immediately. And then you say, oh, no, not that way. Because of gravity. You're being pulled toward one another because of gravity, just like everybody else in the room is being pulled toward everybody else. Because that's Newton's universal law of gravity. So, sometimes you can get away with that. Other times it's, you don't have to, you have to judge your audience. You know, you don't want a shoe thrown at you or anything. So, one time I was breaking up a class, I was the guest speaker into 6 groups, and you know, you don't know their names or anything. So he said, I want you to divide up by birthday. So January, February go over here, March, April there, you know, and one girl just started bawling in the middle. What'd I do? teacher says she's adopted. She claims she doesn't know when her birthday is. You never know. So what, then you get to pick whatever group you want to go to. Even when you don't want to be offensive, sometimes you can be offensive. So I apologize if I'm ever offensive to you in class. It's not intended. Okay. 3-5. Do a couple of those. So let's look at, say, number 4, just for an example. Y equals square root of x secant x plus 3. Y equals square root x secant of x plus 3. So help me out here. What is y prime, or dy dx? Well, what rules do we apply? This is a sum, this is a product. So we apply the product rule to that product. And what's the product rule? It's right here. Derivative of the first times the second plus the first times derivative of the second. So what is the derivative of the square root of x? That's one we did manually following the rule. And it also applies to this rule. Because this is x to the 1/2. This rule says x to the 1/2 becomes 1/2 of x to the minus 1/2, which could be written as 2 square root times the second factor plus first factor times derivative of the second factor. What's the derivative of secant? Secant x tangent x. So that took care of the product portion. And now the derivative of 3 is nada. If you'd like to rationalize denominators, we could. I'll be happy with that. Having said that, since this needing problem is not in the answer book, but the answer book might say something like this: square root of x secant x over 2x plus square root x secant x tangent x. And then we factor secant, so we can say secant of x paren square root x over 2x plus square root x tangent x. Oh, wait, I can do it. Square root x secant x times 1 over 2x plus tangent x. So, when you get to simplifying things, how far you simplify may differ. And the more steps you do in simplification, what's the probability of making a mistake? Okay. Kind of like crossing a minefield, like this. Didn't find one there, so take a step forward. Okay, in a little while you're going to find a mine. That is, you're going to make an arithmetic mistake, you're going to make a factoring error, you're going to do something. So, other than simple arithmetic, I'm interested in, can you apply rules for finding the derivative to get a reasonable result? Look at another there. Let's look at where did I look at one earlier that number 50. Limit as x approaches negative pi over 6 of the square root of 1 plus the cosine of pi times cosecant x. Limit as x approaches minus pi over 6 of the square root of, what is it, 1 plus the cosine of pi times the cosine paren pi cosecant x. Okay. When we're finding derivatives, first thing you should always try is direct substitution. If direct substitution gives you a nice answer, you're home free. Now you kind of have to wonder, do we have differences coming in from the left and from the right? But here we don't. At pi over 6, both the cosine and the cosecant are perfectly smooth functions. So I shouldn't have any issue with that. Okay. So having said that, let's try direct substitution. What is direct substitution? The cosecant of minus pi over 6. Let me ask it another way. What is the, what is the cosecant of pi over 6? And let me ask that another way. What is the sine of pi over 6? Let me ask that another way. What is the sine of 30 degrees? What's the sine of 30 degrees? No, what's the sine of 30 degrees? 1/2. So the sine of 30 degrees is 1/2. The sine of minus 30 degrees, keep in mind that sine is an odd function, sine of minus 30 degrees is minus 1/2. And cosecant is the reciprocal of sine. So the cosecant of minus pi over 6 is, what's the reciprocal of minus 1/2? No, what's the reciprocal of 1/2? Just turn it over. 2. So the reciprocal of minus 1/2 is negative 2. So replace cosecant x with negative 2. And we're now ready to ask about the cosine. What is the cosine of minus 2 pi? What's the period of cosine? 2 pi? 0 to 2 pi? So from 0 to 2 pi or 0 to negative 2 pi, every time you have a multiple of 2 pi, you're back to 0 again. What is the cosine of 0? 1. So now what is 1 plus 1? 2. And what is the square root of 2? The square root of 2. Putting in all the steps, limit as x approaches minus pi over 6, square root 1 plus cosine paren pi times cosecant minus pi over 6, close, is equal to limit as x approaches minus pi over 6 of square root of 1 plus cosine of pi times negative 2, close, is equal to minus pi over 6, equal to square root 1 plus cosine negative 2 pi, which is square root 1 plus 1, which is square root 2. So don't panic just because there's a limit question on the test concerning now sines and cosines and tangents and cotangents and secants and cosecants and
lions and tigers and bears, oh my. So, your yellow brick road